So this is going to be part 4 to section 4.4, and these are some examples where I'll be demonstrating the second fundamental theorem of calculus. So for these 3 examples, there's part A is to integrate to find the antiderivative capital F as a function of x, and then demonstrate the second fundamental theorem of calculus by differentiating the results from part A. So for fundamental theorem, calculus part 2, or the second fundamental theorem, is if f is continuous function, then the derivative with respect to x of the integral with a to x of f of t dt gives you the function f of x. So differentiating the definite integral from a to x of f of t dt gives you the function f of x, which is pretty much the same as the function that you see in the integral sign. It's just variable is changed from t to x. And that's what we'll be demonstrating. So for number 69, so we're integrating, so first off, capital F of x is going to be equal to that integral. Okay, and so I gotta do, part A is going to be integrate. Well, for integration rules, this integral is going to be equal to the integral of t plus the integral of 2. Integrating t, we use the power rule that we've been using in previous videos, where you add 1 to its exponent and then divide by that value, and then that's what that turns into. And then for integrating 2, that's a constant. Anytime you integrate a constant, it becomes the constant times whatever variable of integration that you're using. So this will be equal to, so t to the first power becomes t to the second power, because that's really t to the 1 plus 1. And then you're dividing by that same thing, 1 plus 1. And then integrating 2, that's the constant, so that becomes 2 times t, so plus 2t. And that's the antiderivative, and we evaluate with our bounds, lower limit of integration 0, upper limit integrations x. So this is equal to, and I like to write mine as just 1/2 t squared, and then plus 2t, and then 0 to x. So I apply the first fundamental theorem of calculus, so that I get 1/2, and then replacing t with x, that'll be x squared plus 2x, and then minus f of 0. All right, so that's just our capital F of x minus capital F of 0. Fundamental theorem of calculus, the first part. So the part involving 0, that's all 0, so I can ignore that, and I get 1/2 x squared plus 2x. Now mind you, all of this is equal to capital F of x. So we did that integration to get capital F of x equal 1/2 x squared plus 2x. All right, that's our answer for part A. And now we just apply the fundamental theorem calculus second part. Now demonstrate fundamental theorem of calculus part 2 by defining the derivative. And again, so for the fundamental theorem, it's d dx, and then of the integral from a to x of f of t dt becomes f of x. Now for us, you can think of this thing as being our capital F of x. So d dx of f of x equals f of x. So for us, I differentiate, so f prime of x is the derivative of 1/2 x squared plus 2x and so capital F prime, the derivative of x squared, so you have to remember the derivative rules. So differentiating x to the n is n times x to the n minus 1. So this becomes 1/2 times 2x to the 2 minus 1. Differentiating 2x, well, the derivative of x is 1. This becomes plus 2 times 1. And so capital F prime of x, that's going to be x plus 2. Now notice, so this is our result, what we get for the derivative. Notice in the beginning, we had the integral from 0 to x t plus 2 dt. So this portion is the same function, it's just a variable change. So we've demonstrated that we get the x plus 2, which is really the same function, t plus 2 with a variable change. And that's really what we're doing here for these examples. The next one, number 71, and you're doing from 8 to x of the cube root of t. And then that's what capital F of x is equal to. Again, part A is integrating. Now for cube root of t, that's t to the 1/3. And then integrating t to the 1/3, that becomes t to the 1/3 plus 1. And then divided by 1/3 plus 1. And then our bounds of integration goes from 8 to x. So 1/3 plus 1, that's 1/3 plus 3 over 3, that's t to the 4/3. And then we're dividing by t to the 4/3. Well, when you divide by 4/3, that's the same thing as multiplying by its reciprocal, which is 3/4. So I'm going to go ahead and just write it as 3/4 times t to the 4/3. And I factor out the 3/4 and focusing on plugging in the limits of integration into just t to the 4/3. All right, so that's going to be 3/4 times, and it's x to the 4/3 minus 8 to the 4/3. All right, let's see. All right, then I distribute 3/4. So I have 3/4 x to the 4/3. And then 3/4, so it'd be minus 3/4 times 8 to the 4/3. And I would do 8 to the 4/3 in the calculator, and that's going to be, hold on, 16. It's times 16. So then I do 3/4 times 16, which should be 12, I believe. Yep. So capital F of x, when we integrated as a function of x, it's 3/4 x to the 4/3 minus 12. All right, that's going to be our answer for A. Now, all we got to do is take the derivative, and if we take the derivative and it gives us the original function that was inside the integral, then we know we did this correctly. So now we're going to differentiate. So f prime of x, taking the derivative with respect to x, 3/4 x to the 4/3 minus 12. Well, that's going to become, so 3/4, I factor that out, take the derivative of x to the 4, or x to the 4/3, and that becomes, so you drop down the exponent 4/3, and then it's going to be x to the 4/3 minus 1. All right, using our derivative rules. And then minus 12 is a constant, and taking the derivative of a constant is 0. It'd be plus 0. So that's going to be, so the 3/4 and 4/3 divided, they cancel each other out. So you have x to the 4/3 minus 1. X to the 4/3 minus 1 is x to the 4/3 minus 3/3, which gives me x to the 1/3. Well, raising something to the 1/3 power is the same as the cube root. And that's the result after taking the derivative. And notice at the beginning, we started with capital F of x equaling the integral from 8 to x of the cube root of t dt. So our function inside of the integral is the same as that. It just has a variable change. So at least with this, you know if you did it correctly, if it's when you integrate and then you take a derivative, you get back the function that was inside the integral sign. All right, so the next one, number 73. Okay, and I'll do that off to the side. So it's secant squared Actually, I'll write this somewhere else so it doesn't get mixed in with the other stuff. All right, so that's the problem, secant squared of t dt. And you'd have to know from the integration rules, if you integrate secant squared, that gives you tangent. So integrating this, so the first part is just integrate. So integrating it, you get capital F of x equaling tangent of t, because the integral of secant squared is tangent. And then our bounds, variable, so our limits of integration is pi over 4 and then x. So we apply the fundamental theorem of calculus, and that's going to be tangent of x minus tangent of pi over 4. All right, so this is like our f of x minus f of pi over 4. Or in this case, we're using a function of variable involving t, but we're plugging in x in for the variable t. And then the constant pi over 4. So what's tangent of pi over 4? So tangent of pi over 4, that's sine of pi over 4 over cosine pi over 4. Well, they're both square root of 2 over 2. So tangent of pi over 4 is 1. So this is equal to tangent x minus 1. All right, that's our result for part A. Now we just differentiate for part B. And by the second fundamental theorem of calculus, we should get the same function that's inside of the integral. So we should get that. All right, so integrating tangent x minus 1. So you're going to do capital F prime of x is equal to the derivative respect to x tangent x minus 1. So capital F prime of x, that's going to equal, well, the derivative of tangent is secant squared. So that's secant squared x, and then 1's a constant. So the derivative of a constant is 0. So we get secant squared. All right, so that's the same function that was inside of the integral sign. All right, because we started with, it's pi over 4 to x. Secant squared t dt. So we have the same function, secant squared. All right, and that's it for part 4. I will make a part 5, and part 5 is going to involve finding area.